and welcome everyone to my talk entitled Lattice Boltzmann Simulations for Compressible Flows. First of all, I would like to acknowledge the R&D department at PowerFlow, who is led by Hudong Chen, and I just have the honor of presenting all of the work that has been done there. So let me start with the outline of today's talk. First of all, I would like to give you an introduction to compressible flows. I'll start with a definition and some everyday examples. This will be followed by a section on lattice Boltzmann methods, where I will talk about macro versus mesoscopic description of fluids, how to account for compressibility effects, and how we can extend lattice Boltzmann methods to transonic flows. The third part of this talk is dedicated to validation and application examples. This is split into two parts. The first one is a fundamental section where I'll talk about nozzle flows, compressible shear layers, and shock boundary layers interaction, for examples, while the second part is focusing on applications such as airframe or turbomachinery. This will be concluded at the end, and as Vanessa mentioned, we will have a short Q&A session as well. So let me start with the chapter 1, which is the introduction. So as you all know, compressible flows can be encountered in everyday's application, and the two most prominent things that probably come to your mind are aircraft flying through the air or a rocket that is being launched. And the image on the left shows an aircraft which is not only subject to transonic flow on the outside of the aircraft, but also inside the internal flow in the jet engine is also subject to transonic flow. Some other examples that you might not think of in the first second are shown on the bottom. This is on the left-hand side, you can see the exhaust system of a car, and there also we can have compressible flow inside the muffler. And another application would be high-speed trains traveling, for example, at 300 kilometers an hour. When they enter into a tunnel, there is also strong compressibility effects that need to be taken into account. In terms of the definition of fluid compressibility, a fluid is defined as compressible when density becomes a function of pressure. And this means that compressibility is not a fluid property, because every fluid is to some extent compressible. The compressibility of a fluid is depending on the Mach number, which is the ratio of the velocity the fluid is flowing with divided by the speed of sound. On the sketch on the right-hand side, you can see how we can define different flow regimes based on Mach number. When we're talking about incompressible flow, so where density is not a function of pressure, we talk for flows up to Mach numbers of 0.3. After that, the flow is becoming compressible and density becomes a function of pressure. And this compressible regime can be further subdivided into different subregimes, such as subsonic, transonic, supersonic, and hypersonic as a function of the Mach number. The demarcation between these different regimes is kind of fluid. This is just a rough estimation of where the regime is located. As you might already know, the Navier-Stokes equation can be used to describe the relevant physics. And what I'm showing here on the left-hand side is basically for incompressible flows. The incompressible Navier-Stokes equation are based on equations for mass conservation and momentum conservation. And with the help of these two equations, we can solve for pressure and velocity. If we're now interested in compressible flow, we need to add an energy conservation equation to the set of equation and an equation of state. And with this, we can solve for the four unknowns, which are now pressure, velocity, temperature, and density. Now let's talk a little bit about lattice Boltzmann methods. As an introduction, let's look at the scales of a fluid. I'm showing here a cubic volume where the red dots inside the volume indicate molecules. And as an example, for 1 cubic centimeter of air, we would look at a total number of 10 to the power of 19 molecules. Now there are different ways of describing the fluid: the microscopic scale, the mesoscopic scale, and the macroscopic scale. In the microscopic scale, we would look at the, well, this should actually, yeah, no. At the microscopic scale, we would look at the movement of each particle, which is described by the kinetic theory. And doing this for all of the molecules that we are finding already in this 1 cube centimeter of air is just too much computational effort that would be needed. So another way of looking at that would be to look at the mesoscopic scale of the fluid, which basically is the probability to find is basically to look at the probability of the molecules. And this is described by the Boltzmann equation, which can be derived by statistical mechanics from the kinetic theory. The third one on the right-hand side is the macroscopic description of a fluid, and this is probably what most of the people are familiar with, because these are the Navier-Stokes equation, which are based on a continuum description of the fluid. The Navier-Stokes equation can be derived from the Boltzmann equation through the Chapman-Enskog expansion, and this is something important that I would like you to keep in mind, because we will come back to that in a second. So what does the Boltzmann equation look like? So each particle occupies a point in phase space, which is the combination of position x and velocity v. And now we can define a distribution function f that provides the probability to find a particle at location x and time t with velocity v. What Boltzmann suggested was to say that instead of solving the movement of each particle, we would like to come up with an equation for the probability distribution function, and that is derived from the following equation below, that the total change of the distribution function due to transport must be the total change due to of the probability density function due to collision. And writing that out will give you the Boltzmann equation. The first term is the temporal change of the distribution function. The second term is the convective change of the distribution function. The third term is a term that is due to external forces. And on the right-hand side, we see the collision term omega. For now, we would like to neglect the body forces so that our Boltzmann equation simplifies. What we can do next is then discretize the Boltzmann equation. And by doing this, the equation is shown here. So basically, we discretize in space and time. And by knowing the distribution function at location x and time t, plus the collision term at time x and time t, we can calculate the distribution function at a later time step. The collision term on the right-hand side is typically approximated by the Badnaga-Gross-Krog model, which is called BGK. And this collision term omega reads as the difference of the distribution function and the equilibrium distribution function divided by a relaxation time tau. This collision term, or this relaxation time tau defines a time scale of how long it would take for the fluid to reach equilibrium. And this relaxation time tau can now be used to couple to a turbulence model. So by replacing tau with an effective relaxation time, we can say that the effective relaxation time is the molecular relaxation time, which is directly related to the viscosity of the fluid, plus a turbulence relaxation time. Once we solve for the probability distribution function, we can extract macroscopic quantities that we are interested in, like density, temperature, and pressure, from the moments of the distribution function. I'm just showing two examples of how to obtain the density from the distribution function f, or how to obtain the kinetic energy from the distribution function f. And there are many other moments or integrals that can be used to calculate the different macroscopic quantities that an engineer is typically interested in. So now let's move on to the lattice Boltzmann method. The difference to the Boltzmann method that I showed previously is that the continuous velocity space is now discretized into a limited set of velocities that I call here v with a subscript of I, which corresponds with corresponding distribution function fi. So basically the equation that you see here is the same as previously, just now that we added a subscript I that is valid for all of the discretized velocities. In the incompressible formulation, the D3Q19 model is typically used. What this means is that a three-dimensional space is discretized into 19 discrete velocities. And you can see these 19 discrete velocities in the sketch shown on the right-hand side. And this formulation conserves mass and momentum, and the compressibility error scales with Mach squared. And if you remember, we said that the compressible flow limit has a Mach number of up to 0.3, and so your error scales with 0.3 squared, which is 0.09. So up to that Mach number, that's where we say typically that compressibility can be neglected. Typically, a Cartesian lattice is most commonly used. The lattice Boltzmann method, as you see from the equation, is unsteady by definition, and we have a one-to-one advection. So from one lattice to the next one, there is a direct advection, which means that we end up with very low dissipation. So now I would like to talk about the compressible Boltzmann method. As I said previously, there are different numbers of velocity states possible, and the one that I showed you before is the D3Q19, so I'm just showing that sketch again. And if you remember, using the Chapman-Enskog expansion, we can arrive at the incompressible Navier-Stokes equation. Now, there are different ways of discretizing the velocity space, and another way of doing this would be, for example, the D3Q39 scheme, which is shown here on the right-hand side in the center of this slide, where you can see how 3 different lattices are combined, and we end up with 39 velocity states. Using the Chapman-Enskog expansion here basically would lead to the fact that we can simulate compressible, we would be able to recover the compressible Navier-Stokes equation, and we would conserve mass and momentum. But if you remember, for a truly compressible flow, we would also need the energy equation. And that one could be achieved by a model, for example, that is the D3Q121, for which I do not have a sketch here. But yeah, you can imagine how many lattices this would need to recover 121 states. And by using the 121 states and the Chapman-Enskog expansion, we would be able to recover the compressible Navier-Stokes equation and conserve mass, momentum, and energy. However, as you can already see here, by increasing the numbers of states from 19 to 39 to 121, the computational cost of the method would grow very much and we would lose the advantage. So what has been developed is the following hybrid approach, and that is basically coupling an LBM momentum solver with an energy equation. So in order to maintain the computational efficiency of the lattice Boltzmann method, the D3Q39 model can be coupled to an energy equation, as I said, instead of using the full D3Q121 model. Now, this has been developed in PowerFlow over more than 15 years, and I'm just showing like a short history of how the coupling to an energy equation historically evolved. this started with a partial differential equation for entropy. The next step was to couple the LB momentum solver to a Lattice-Boltzmann-based scalar equation for entropy. And now with the latest release of PowerFlow, we have the momentum solver coupled to a Lattice-Boltzmann-based scalar equation for total energy. And yeah, I'm just citing two papers at the very bottom, and where you can see that this activity has been going on for a long time. And right now, we are at the stage where we can couple to a total energy equation that is based on a Lattice-Boltzmann scheme. So how does this now enable us to simulate high Mach number flows? The hybrid approach that I showed you earlier, where we couple the high order D3Q39 scheme with an additional energy equation, provides stable results for a Mach number, which is, just give you the definition again, the maximum velocity over the local speed of sound of 0.94. And now the question becomes, how can we come up with a scheme, or how can we change the simulation approach to allow Mach numbers greater than 1? And there are two ways. The first one would actually be to increase the maximum velocity for which the scheme remains stable, but this would result in a computationally more expensive method. And the other way of doing this would actually be to decrease the speed of sound. And the second option can be realized by an interaction force in the LB equation. So basically, this results then in a compressible Lattice-Boltzmann method that is robust, accurate, and efficient for flows with Mach numbers reaching 2.0. The 2.0 limit is not a hard limit, but it has been chosen for what is available in PowerFlow because of the trade-off between accuracy, speed, and robustness. And so in general, higher Mach numbers are possible, but this would result in a penalty on efficiency. Now, the PowerFlow solver, which is one of Simulia's Lattice-Boltzmann methods, has two unique components. The first one, as I mentioned earlier already in the summary, is basically that we have a Lattice-Boltzmann-based fluid dynamics solver, which has critical differences from a generic LBM. As I said, we have high order. We have a high order method, regularized collision operator, and we're using a Lattice-Boltzmann-based energy solver for transonic flows and a patented surface treatment. This describes a fully realizable microdynamic system with low dissipation, which is highly time transient and highly accurate, and we can ensure physical boundary conditions. The second key component to PowerFlow is the turbulence model, which is called VLES. And this is a different paradigm thinking of turbulence modeling. It relies on self-organized criticality, which means that for all flow cases, we just apply one turbulence model without changing a parameter. From a phenomenological description, this turbulence model reduces Turant's result in steady, attached, or homogeneous flows. And we also include an extended War model to account for pressure gradients. Since this e-seminar is focusing more on the compressible aspect of LBM, if you're interested more on the turbulence modeling side of PowerFlow, there is a Simulia on Demand e-seminar, which is called Scale Resolving Simulations for Industrial Design. Okay, this was already the section on the Lattice-Boltzmann methods, and now I will go through some validation and application examples. First of all, let's start with a very simple case, which is a converging diverging nozzle. You can see the geometry in the top left side of the slide. And basically, this is a one-dimensional case involving a flow of an inviscid ideal gas. And this test case is used as a standard validation and verification test case because an analytical solution exists. By reducing the static outlet pressure, PS out, we can, a shock is being created in the diversion portion of the nozzle. On the right-hand side, I'm now showing the pressure, density, temperature, and Mach number distribution along the center line of this nozzle for a static outlet pressure of 0.75. The red line is the simulation from PowerFlow, and the black line is the analytical solution. As you can see, we have a very good agreement with the analytical solution, and you can also see that the maximum Mach number that we're reaching inside the nozzle is slightly above 1.6. One comment on the spikes that we see here, very close to the shock interface. For all numerical methods, even if they are based on Navier-Stokes equation, since the shock is shows a discontinuity, there might be some small oscillations that occur close to the shock interface. A second basic flow validation case is the compressible shear layer. So what you see here are two flows that are mixing with a fluid interface. We have a high top Mach number flow and a low bottom Mach number flow. And this test case was actually part of NASA's 40% challenge, where they invited people and researchers from everywhere to participate and increase the accuracy for this test case. And basically, what we can now look at as a first step is to look at the velocity profiles at these 5 different sections. When we plot them and scale them accordingly, we can see that starting from the second velocity plot, all of the velocity profiles are collapsing to one single curve, which corresponds well to the experiment. So this means that the flow that we are simulating here is giving the correct results. The curve at the very beginning just shows the initial state of the shear layer, which is not mixed out. But then once we travel downstream, the flow starts to mix, and then we end up with a well-defined curve. Now, what we did is we looked at the compressibility effects in the shear layer. And what this means is that the compressibility reduces the shear layer growth. So the higher the Mach number difference, or the convective Mach number as defined here, the longer it will take for the shear layer to grow. And in the right-hand side, I'm showing 2 PowerFlow simulations for 2 convective Mach numbers, the red circles, the first one at a convective Mach number of 0.46 and the second one at a convective Mach number of 0.7. And what the y-axis shows is basically the growth rate relative to an incompressible flow. So for incompressible shear layer, the growth rate would be 1. The factor would be 1. And then as compressibility starts to become important, the shear layer starts to grow more slowly. And the 2 PowerFlow simulations are right within the data. So it shows that the compressible LBM approach that we are following here is giving the right answer. Another fundamental test case is a planar shock wave impacting on a wedge. And what you can see here in this animation, once I'll start it, is a planar shock wave, so this black line, traveling with a Mach number of 1.34 over the wedge, which is the red triangle. And what we are showing here is the density, the magnitude of the density gradient. And once the shock impacts the wedge, yeah, you can see a lot of reflections from the geometry, from the boundary, and we start to see the vortex shedding appearing. And we are now interested in, I'm going to stop this animation here, in 2 points specifically in the simulation, the triple points. And the triple points is basically the line where we have two shock waves meeting each other. So we have two triple points in the simulation. The first one is at this location, and the second one is here. And what we can do is we can plot the evolution of this location over time. And the power flow results are basically the red line for the upper triple point, and the green line is the location of the triple point, that is the lower one here. And if we overlay with the experimental data, we can see that the direction in which the triple point travels is correctly captured with power flow. Now coming to another interesting test case, which is the axisymmetric transonic bump. This is again part of NASA's 40% challenge. And what we are now encountering is a shock-induced separation. And I'm going to play this animation here. What you can see here is the flow over a cylinder on the outside of the cylinder, and where we have a transonic flow region where Mach is greater than 1, we have a shock, and then downstream of the shock, the flow is separating. When we compare now the pressure distribution on the bump for 3 different simulations where we vary the mesh density, coarse, medium, and fine, we see that we are getting good agreement with the experimental data, which are the black crosses here. We can now look also at time average velocity profiles on the bump. So these are different locations on the bump. The bump geometry basically follows this line here. And what you can see here is that we have, in general, a good agreement with experiment for all 3 resolutions. But if we zoom in a little bit more into the region where the flow is separating, so at station 7, for example, and also in the flow recovery, we can see that the fine resolution is able to capture the velocity profile close to the wall fairly well. Since this is an unsteady simulation, we are also interested in the velocity fluctuations. So I'm plotting here U prime, V prime on the different location as above. And while there might be some under prediction in the maximum level, there is still a good agreement with experimental data also for the higher order time statistics. Now we're moving to a test case, which is a transonic cavity. As you can see from the geometry, we have a rather deep cavity where the flow is traveling over with a speed of Mach number of 1.35. And when this happens, we have a shear layer developing, as you can see here, and this shear layer becomes unsteady, starts to flap, and is basically interacting with the backside of the cavity. To give you an idea of the mesh size, we are using roughly 40 million voxels, so volume elements in the Lattice Boltzmann method, and it takes about 20,000 CPU hours to simulate 0.7 seconds of physical time. The image on the bottom shows you the resolution of very small scales inside the shear layer, and this is being achieved with a VLES turbulence model. What we are interested in now is basically the fluctuation pressure on the cavity bottom. So this is a plot of the cavity floor from 0 to 1, where we're looking at the fluctuation levels that the pressure has. And the simulation data in red overlaid with the experimental data in black shows a good agreement. And as we would expect, if I play this again, the further we move down, the higher the pressure fluctuations get because of the unsteady and unstable shear layer that is developing there. For this test case, we also have power spectra. So what we're looking at here is basically a view of the cavity from the top, and on the floor of the cavity, we have different probes, and we are measuring the pressure as a function of time, and then performing Fourier analysis, and doing this both for the experiment and the simulation. We can see that we are getting very good agreement between the experiment and the simulation, and we are recovering some characteristic modes that are related to the flow speed and the size of the cavity. I also have a couple of more power spectra that I can show here, and yes, you can basically see that the agreement between experiment and simulation is very well, and it's kept throughout the entire cavity. Another interesting test case is a nozzle with a fluidic thrust vectoring. What this means is shown in the image on the top left. We have a primary nozzle flow where the blue arrow is pointing at, and we have a secondary flow through a very, very tiny injection slot. And how this can be used is by injecting a mass flow into the nozzle. We can actually turn the jet into a desired direction. And just to give you an idea of the nozzle expansion ratio, it's 1.9. The nozzle pressure ratio, so between inside and outside, is 4, so a very high pressure difference, leading to very high Mach numbers. And we're looking at 4 different mass flow ratios. So the mass flow ratio between the secondary flow and the primary flow, so very small number, 0.025, going up to 0.1. And how this looks like, for one example, is shown here. We can see shock waves and expansion waves inside the the jet that is appearing, and due to the ejection of the secondary mass flow, we are able to show that the jet is turning into a desired direction. In terms of resolution, we ran this case for three different levels: coarse, medium, and fine, where the numbers of cells range from 25 million up to 200 million. And the CPU hour, just to give you an idea of the cost, ranges from 6.3 thousand CPU hours to 72,000 CPU hours. When we now look at the different mass flow ratios, so again, if you remember, the small value means that the little jet that is ejecting into the nozzle has a very small mass flow ratio, and has a very small mass flow, and the larger value has a large mass flow. We can see now how this is impacting the shock structures that are appearing inside the jet. And also here we have some comparison to experimental data. On the x-axis, we have omega, so the mass flow ratio, and to the y-axis, we have the pitch angle, basically the deflection of the jet. And here you can see that the experiment in black and power flow in green show a very good prediction of the trend. And these are all results for the medium resolution. Now I will talk about transonic airfoil simulation. This is the Honora transonic airfoil 15, which we simulate at a Mach number of 0.73 and a Reynolds number of 3 million with an angle of attack of 3.9. And the interesting thing here that is happening here is that we are running into transonic buffet. And what this means is, if I play this animation, that we have an interaction between the transonic flow region, which is this brown isosurface, and the flow separation that is induced due to the strong shock on the airfoil surface. And this basically creates a oscillatory movement of the shock. And what I'm plotting on the left-hand side is the lift curve, is the lift as a function of time corresponding to the image that you see on the right. And yes, as you can see, with this condition, with this angle of attack of 3.9, we are in a in the buffered region because the shock movement is sustained. What we are now interested in is the buffet onset. So when does buffeting actually start? And this is characterized typically by the amplitude of the pressure fluctuation that we would measure on the airfoil versus the angle of attack. So I'm showing on the right-hand side a plot where we have the angle of attack of the airfoil and the maximum pressure fluctuation that we are encountering on the airfoil. In black is the experimental curve, and in red is a two-dimensional power flow simulation, and in blue is a three-dimensional power flow simulation, which is essentially what I showed you on the previous slide. The two-dimensional simulations show a very abrupt and early onset, so we basically have no buffet at 2.5 degree angle of attack and then full buffet already at 2.7 degree angle of attack. And this is due to the fact that we're running 2D. We are not resolving any span-wise, any small turbulent structures, and this gives wrong results. When running with a 3D simulation, our results improve. The slope is much more accurate than it was for the 2D results. And the question that now remains is, why do we have this offset? And because if we look at the pressure distribution for one angle of attack from the experiment at 3.5 degrees, so at this angle, for example, we can see that when we take the corresponding power flow simulation at 3.9 degree angle of attack, we get a good agreement with the experimental data in terms of CP and in terms of the pressure fluctuation on the surface. And this would basically mean that there are some wind tunnel installation effects that we are not taking into account by our simplified setup, which is just an extruded 3D, which is just an extruded 2D airfoil. Now we're coming to the more application example. So I'm showing you here the NASA CRM, which is a commercial aircraft that was designed by NASA and Boeing for research purposes. And we ran this geometry at a Mach number of 0.85 and a Reynolds number of 1.5 million. This resulted in a mesh of roughly 100 million voxels, and this one simulation costs about 10,000 CPU hours for 508,000 time steps. And we simulated cruise condition, so where the flow is attached, and also buffeting conditions, which I explained to you earlier what that means. I'm now showing the lift polar on top and the drag polar at the bottom. The power flow simulations are the blue points, and in the linear range, so around cruise condition where the flow is well behaved. And this is done for a configuration with the wing and body only. So we do not have the tail in the simulation, whereas at the buffet conditions, which appear at higher angles of attack, we included the tail, because that's what was done also in the wind tunnel. And as you can see, we are getting good agreement not only in the range around cruise conditions, but also in the buffet region. When we now look at the pressure distribution in the linear range, so this is showing 3 pressure cuts on the wing as we cycle through 3 different angles of attack from 2.75 to 4.0. In the linear range, we can see a good agreement with experimental data at a very good agreement with experimental data at the inboard and midboard location, and there appear some discrepancies between the wind tunnel and the power flow simulation at the tip of the wing. But this is a known issue because the shock position on the outboard wing is affected by the sting support system, which is the support system that is holding the model inside the wind tunnel. Since we also ran this CRM simulation at buffered condition, I'm showing now the pressure distribution from the simulation on the left-hand side, power flow, compared to experimental data. And so the right-hand side of the picture is from the wind tunnel, where JAXA used a technique that is called pressure-sensitive paint. So the paint changes its color or its reflection. Basically its color in the end, and we can compare then the wind tunnel simulation to the wind tunnel to the simulation. And what you can see here is a very good agreement in terms of shock front, how it changes, and because the shock front is basically the crisp line between blue and green, as you can see here. What we can also compare to from the wind tunnel and from the simulation is basically the pressure fluctuations along this line. So what I'm showing here in this plot on the top right is along this chord location from leading edge to trailing edge, we can calculate the power spectral density of pressure on each point and then plot it as a function of frequency. And by doing this, we can see where there is a large change in pressure on that line, and also in which frequency range this is happening. So the red area shows that there is a lot of pressure fluctuation happening, which is close to 0.2, so very close to the leading edge of the wing. And also in the frequency range, so basically from a low frequency up to 1000 hertz. And by comparing the power flow simulation with the wind tunnel results, we get an excellent agreement here. So this brings me to the last test case, which is now a turbo machinery test case, which is known as the STT fan, which is based on the GE NASA fan stage model. There are 3 different operating conditions: approach, cutback, and sideline. And this results in fan tip speeds of 228 up to 370 meters per second, so well into the transonic flow regime. The image on the right shows the geometry. The fan blades, we have 22. There are 3 different types of OGV geometry. For what I'm going to show you next, we are just showing you the baseline geometries, which is the 54 vanes, which is shown at this instance in time. In terms of simulation time or mesh sizes, also here we have different grid resolution, coarse, medium, coarse, fine, and some extra fine resolution near the rotor. This leads to mesh sizes ranging from 430 million elements to 953. Keep in mind that this is a simulation of the whole 360-degree engine. So we are not just looking at one passage, but it's the whole 360-degree engine. And the turnaround time on 1,000 cores, as an example, for the core simulation takes 1 day, the fine 2.5, and the extra fine takes 5 days. What we are then getting in terms of shock structures is shown here in this image. This is basically the Mach number, where red is a high value and blue is a low value. And you can very nicely see how the shock waves are sitting on the blades and how they are propagating upstream. For the 3 operating conditions that I showed you earlier, we can plot the fan pressure ratio versus the mass flow, and we can see the 3 blue bullets which represent the power flow simulation. There's a very good agreement with the experiment, and the highest simulated point that we ran was slightly under 100% of the nominal RPM. Now we also here have some nice experimental data that we can compare our results to. The top row is the experimental data. The middle row are the power flow results on the fine grid. And at the bottom, we calculate the difference between the 2 of them. The quantities that are shown from left to right are streamwise velocity, spanwise velocity, streamwise velocity fluctuation, and spanwise velocity fluctuation. And I'm showing this for 2 different locations, one close to the fan and the second one close to the OGV. And as you can see, there is some overprediction of the wake deficit with power flow, for example. So this blue line, or this area here, is a darker blue than this area. But what is really well captured are the unsteady or the velocity fluctuations in the wake for both stages here, left and right. Okay, this brings me already to the final part of this presentation, which is the conclusion, and then we will have some time for Q&A. So as a conclusion, Simulia Power Flow has a differentiated LBM solver, and it is differentiated in the way that it has a high order scheme that recovers the compressible fluid dynamics while maintaining the computational efficiency. And this is basically being achieved by coupling to an LB energy equation, which also ensures exact energy conservation on top of mass and momentum conservation. This is achieved by the use of an interaction force that extends the Mach number range of up to 2. And again, this is a trade-off and not a hard limit. Other features of power flow include an easy mesh generation and fast turnaround time. I did not go into details on that, but there are other e-seminars that highlight that, or if you have questions, yeah, please feel free to reach out to us. The ability to handle very complex geometries. What I've shown here are still fairly simple geometry for A&D cases typically, but PowerFlow has the ability to handle complex geometries. And also the accuracy of the results are very high due to our proprietary VLES turbulence model. This means that one could use PowerFlow to reduce the number of typically expensive physical tests, or to enable simulation-driven design decisions by gaining insight into the flow physics that are in some cases not even accessible during physical tests. And yes, with that, I conclude my talk, and thank you very much for your attention.